Welcome to this RF Industry Icon podcast. I'm Pat Hindle, and this episode I'm talking with Fred Daum, who is the IEEE Fellow, a Principal Fellow at Raytheon, a distinguished lecturer for the IEEE, and a graduate of Harvard University. Fred was recently honored with the 2024 IEEE Dennis J. Picard Medal for Radar Technologies and Applications for his research, design, development, analysis, and testing of complex phased array radar systems, making them work in the real world. And this was done at the prestigious IEEE Honors Ceremony in Boston that I attended. So it's great to connect with Fred there. He has developed and analyzed and tested the real-time tracking, waveform scheduling, calibration, and discrimination algorithms for essentially all the long-range phased array radars built in the US in the last 4 decades. So is definitely a top expert in the RF industry field and an icon that we're going to talk to today. Welcome, Fred.
Thank you very much, Pat. Glad to be here.
So let's start off kind of early in your career. What made you pursue a career in science and research? Where did that interest originally develop?
I think it went way back to when I was just a kid. Even in kindergarten, I can remember wondering, what is heat? What makes things hot? And what makes things cold? I was generally curious about the world. And then later, as a little boy, I would play with chemistry sets and build stuff out of simple electrical circuits. And one influence, I think, may have been a TV show called Mr. Wizard, which really was a wonderful program. It was designed specifically for children. Mr. Wizard would do scientific experiments and show us electrical and chemical and mechanical wonders of the world and explain how they worked, and would ask questions. And it was quite stimulating. And then in elementary school, I had a 5th grade teacher, Mr. Vitale, who encouraged my interest in things like science. And finally, in 6th grade, we were all asked to give a talk for our class. And I picked Albert Einstein as the subject of that talk. And as part of it, I attempted to explain to my fellow 6th graders what the general theory of relativity was. Of course, I didn't really understand it myself, but I explained it at about the level of an Encyclopedia Britannica article or a Scientific American article. And so that stimulated my interest, desire in learning more, like what is a differential equation and what is the real physics. And then in 7th grade, my math class, we studied set theory and Boolean algebra. And one of the things they told us that it was useful for was building computers. So naturally, I was curious about, what is a computer? What can it do? Can I build it? So I actually built one, a little simple digital computer. And I was surrounded, my very best friends were all interested in science and math also. So we stimulated each other. And we could read things like Scientific American, and then books like 1, 2, 3 Infinity by George Gamow. And Bertrand Russell wrote a little paperback book called The ABCs of Relativity, about general relativity, which is quite readable by a 7th or 8th grader. So the world was full of science, and I was full of curiosity about that. I think that's the reason I became interested in science and research.
Yeah, wow, that developed really early. So it must have been fun explaining it to 6th graders, Einstein's theory of relativity.
Yeah, but they didn't ask any good, tough questions.
You had the wrong audience for your what level
Well,
you were at.
it was actually a pretty good audience. These kids
Okay.
were very smart.
And so you went to Harvard University. Can you tell us about your college years and any interesting stories you had from that time?
So surprisingly, I think the most useful thing that I did when I was an undergraduate was I was on the debating team. And this was terrific practice, standing up and giving talks, getting lots of feedback from the judges. I mean, you either won or you didn't win, and the judges would explain why. And well, we debated with other schools like Princeton. Princeton came in against us with with I don't know, about six huge long drawers of 3x5 cards with ostensibly information and facts and arguments that would destroy our arguments that we were making in the debate. And after thinking about it a while, I could see that Princeton wasn't really making much use of these cards. And I thought, well, let's just do intimidate us. So I was just having fun rather than being intimidated. And then another team that we debated was this was a debate at Swarthmore College. Lots of teams went there, but one team was from a penitentiary. I think it was called Lewisburg State Penitentiary in Pennsylvania. And it turned out that Jimmy Hoffa, the famous union leader and felon, was in that penitentiary, and he was the coach of the debating team. And actually, their team was pretty good.
It's interesting.
Oh yeah, that was cool. That was great. They didn't intimidate us either, though. No,
Then you
no,
must have
no.
been good.
Well, we were intimidating. Actually, it was always a team of two people, me and a partner. And my partner in one debate told me the other side was intimidated just by looking at me. I don't know how that happened, but
You had a
that was
good game
really great.
face, I guess.
Yeah, I think so. And then later at Harvard in graduate school, it was like being in heaven because I was surrounded by all of these superstars in research, in math, like Barry Mazur, George Mackey, Andy Gleason, David Mumford, Raoul Bott, and Roger Brockett and Larry Ho. And Raoul Bott was an interesting mathematician. His training was as an electrical engineer. So I related to him. He would also not be afraid of asking questions. At a math colloquium at Harvard, sometimes, even though nobody's understanding what the speaker is talking about, they're afraid to ask a question. And this goes not just for Harvard, but all sorts of other places. But Raubot was fearless and also very smart, and he would ask questions to help other people in the audience figure out what was going on. He could tell when nobody was understanding. And this is a group of world-class mathematicians. So intimidation was on the menu at Harvard. That's one thing I learned.
And so then you worked at Raytheon all these years. Can you tell us about the early years at Raytheon and how your career steered you toward radar?
Well, it was unavoidable to get into radar. I was surrounded by many different kind of radars at all sorts of frequencies: X band, S band, C band, L band, UHF, HF frequencies. Shipboard, the Air Force, and on for the Army, and you name it, we built it. Even for NASA, for space missions. So the very first radar I worked on was a little X-band phased array, a limited scan phased array called ANTPN-19, which was a for the Air Force, and it was a tactical system that was used to land aircraft. It was an air traffic control system for the Air Force. And Dave Barton was the radar system engineer who had conceived the architecture of the radar, the antenna. It was a limited scan, very, very clever Cassegrain antenna. And I learned a huge amount working on that program. I programmed the computer to control the whole radar system in real time. I coded the tracking algorithms, the radar waveform scheduling algorithms, the beam pointing algorithms, and the real-time executive, because this was the old days. This was a bare machine. This computer was actually the Apollo guidance computer. It was a beautiful 32-bit mini computer, and I program it in assembly language. a very low-level language, very primitive operations like fetch, store, and, or, add, two numbers, shift right, shift left, etc. And you had to tell it where to put stuff in memory and how to fetch it. So it was phenomenally great for me to be learning about radars and computers all at the same time. And then after that, as I said, I was completely surrounded by radar systems of all sorts of different types, as well as world-class radar experts like Dave Barton, Eli Bruckner, Fritz Deutel, all three of whom won the same Dennis Picard Gold Medal from the IEEE before me, but also Hal Ward, Bill Schrader, Herb Grzinski, Wilhelm Grigors Hansen, and many, many other wonderful, helpful people. That also was like being in heaven. It was a fantastic learning experience to learn about the radars, the physics of the radars, learn about computers, learn about algorithms, learn about real-time software development. It was great. So I liked it.
Yeah, I used to enjoy talking to Eli. He was a pretty funny guy. He used to write some articles and do some webinars for us.
Oh, yes.
So, how did you develop an interest in filter theory and algorithms?
This is a fun story. I was working at Bell Labs one summer when I was after my junior year in college. I got very nice summer job in Whippany, New Jersey. And I was doing experiments for a physics group on IR, passive IR sensors. So, but in the same laboratory, they had lots of lasers around. So the protocol of Bell Labs was to be safe and have everybody get a baseline eye exam, photograph of your retinas. So apparently there was no place to do this well enough in New Jersey. So they shipped me off to Manhattan to a eye specialist in Central Park South. So I took the bus to Manhattan, walked up Fifth Avenue towards Central Park. I spotted the Doubleday bookstore on Fifth Avenue, and I had plenty of time to kill. So I went in and found this book by Norbert Wiener called Cybernetics. And I was thumbing through it, and in the middle of it, there's this inscrutable mathematics that apparently corresponds to the Wiener filter, which is a predecessor to the Kalman filter, which is a predecessor to more general nonlinear filters. So I didn't know any of that. I'd never heard of it before. So I bought the book, read it, and decided I'd better learn about, or I deeply wanted to learn about Kalman filters. So then, just before I entered Harvard, I bought a textbook by Bryson and Ho that was extremely clear. And I read it and learned all about Kalman filters. Kalman filters are sort of the basic example of a good algorithm that can be used as the basis for designing nonlinear filters. Like we call it the extended Kalman filter, actually. So at Harvard, I did my thesis on nonlinear filtering theory, very, very advanced. I was trying to invent new exact nonlinear filters. But then at Raytheon, after that, it turns out they had an intense desire to apply this theory because their customers were telling them they had to, and their competitors were breathing down their necks. So I was almost the only person in the whole place who knew what a Kalman filter really was. So that was great to have this theory that I liked to be valued at a place that I worked. And at Harvard, you could take any course you wanted, also at MIT. For example, Harvard at that time had no courses, believe it or not, in artificial intelligence. So I rode my bike down to MIT to take Marvin Minsky's course in artificial intelligence from Marvin Minsky. and Seymour Papert. And that was a fantastically good thing to do. And then after, I mean, otherwise at Harvard, I studied Bayesian decision theory, estimation theory, lots of numerical methods. So I was just completely surrounded by a rich environment of algorithms.
Well, that kind of brings up my next question. You know, you seem to be a very practical engineer and also a deep theoretical scientist. You know, how did you develop skills on both sides? Because it seems like people kind of go one way or the other.
So I am a member of both tribes. I think of this question as sort of a tribal question. You've got theorists and then practitioners. But I am a member of both tribes. As an undergraduate, my degree is electrical engineering, which is pretty practical. You know, I designed real electrical circuits and made them work. I was designing neural nets, even as real physical analog neural nets as an undergraduate. So I was pretty practical based on my undergraduate education. And of course, at Raytheon, it's very, very practical. You have to build stuff that really works. And then at Harvard, I mean, I was taking courses from world class mathematicians at Harvard. So I was immersed on both sides of the coin. And all throughout my education, I pursued as much math and as much physics as I possibly could. And I was encouraged, I always took honors courses every semester, either in junior high school, undergraduate, etc. And I think that really, really pays off. It allows you to cut through things and understand things and really work on them at a deeper level a lot faster. Another thing related to this two cultures idea is there are a lot of pure mathematicians who really look down on applied mathematics. In fact, there's a famous essay written by Paul Helmos. The title of the essay, believe it or not, is Applied Mathematics is Bad Mathematics. And that was sort of like a slap. Well, firstly, at the time he wrote that essay, everybody knew it. It was quite obvious. It was manifest all over the place. And in fact, in German, the term is schmutzig mathematics. Dirty mathematics is what they referred to as applied mathematics. But I do not suffer from that disease. And I think that helps.
So, turning back to radar, you developed, analyzed, and tested the real-time tracking, waveform scheduling, calibration, and discrimination algorithms for essentially all the long-range phased array radars built in the US in the last 4 decades, as I mentioned in the opening. You know, how do you go about this process of doing this with a radar system? I mean, what are the key things that you're looking for?
So the starting point for me is a system engineering approach where you start by reading the requirements, the customer's requirements. These are typically quantitative, detailed specifications written down in black and white, written in complete sentences, very quantitative, with models, with specifications of what's the probability detection, what's the tracking accuracy, how fast do you have to do things, how many targets do you have to handle, what kind of targets, what size of targets, what ranges, everything that you would, much of the information that you would need to design to understand the requirements to design the system. But in addition, of course, you have to know what the customer really wants by talking and listening actively. And another component is cost and schedule. So we have requirements, performance requirements, but also cost and schedule. And all three of those have to be balanced. The customer only has a limited amount of money and a limited amount of time. And so you cannot gild the lily, you cannot give the customer your favorite pet rock, you cannot make it the way you think, even though it may not be required in some cases. So it's a very interesting sociological, psychological game to navigate these trade-offs between requirements, cost, and schedule. And as you can imagine, the managers have a different emotional orientation than the working engineers. So there's often a battle. And I could, if I wanted to, tell you some pretty spicy stories about battles, including with Dennis Picard himself, who this prize is named after. But after that, you have to do a lot more. You to develop these algorithms for these radar systems. You have to thoroughly understand the physics of the radar and the targets and the environment. And the environment, I mean, it's not just white Gaussian noise. It's clutter, it's jamming, it's interference by radio stations, cab drivers' radios, television stations, microwave ovens. One of the biggest sources of jamming of a certain very important radar system that I could tell you about at 6 o'clock around San Diego, they noticed that the interference level goes up dramatically, which is when people come home and start dinner with their microwave ovens. Now, a microwave oven might only leak 1 watt of S band energy, but if you add up the millions of people around San Diego who have their microwave ovens on, you've got a megawatt floating around, which is not great. So that's another shock. Another key ingredient is robustness. So that's a word that gets bandied around in statistics and AI, and but in the context of making real radar systems work, it comes down to very, very serious issues such as, well, please make the system work, despite the fact that the conditions for the radar, the targets, and the environment were not specified by the user. They were not in the spec. They were not something that you ever tested or even planned for consciously. And these sorts of things include jamming, clutter, multipath, interesting physical phenomenon with rocket exhaust plume and wake and all sorts of other great stuff. It's in refraction, anomalous refraction from the troposphere, like ducting. So these things might never be mentioned in any specification, but nevertheless, we know that what the customer really wants is that the system really work. Now, there's only a limit to that. You can't build a system that will be guaranteed to work under all conditions for all unknown unknowns that the world might throw at it. But still, you absolutely need to work very hard on robustness. And I think my training as an electrical engineer helped me a lot, because when you design a real electrical circuit, you have to consider robustness. Another big important issue is both the real world testing of the system as well as the Monte Carlo simulations. You can't test a radar system under all the conditions of interest in the real world, because those kind of tests would be just too expensive or dangerous, like simulating World War III. I mean, you can't do a real world test of put a lot of effort, time, care into designing very detailed Monte Carlo simulations to test the algorithms and the entire system, including the hardware, before we declare the system is ready for real world performance. Real world testing is the most fun for me because you always learn something. You always have new problems that come up, things that you've never seen before. The ones you've seen before are sort of boring and you dispose of them very quickly. But the new things are fun. It's sort of like solving a puzzle, because some problems might be in the signal processor, some problems might be in the antenna, Some problems might be in the receiver or the transmitter, and it's not clear where the problem is. Some problems might be in the software or interfaces between the radar hardware and the computer. So I guess in summary, you could say the whole process of developing algorithms and making complicated radar systems work in the real world is it's like physics. It's a combination of experiments, real world experiments, and theory that help you guide you along the way.
Yeah, it's a very complicated system, so I'm sure there's a lot of things that can go wrong.
Helps to understand it.
Yep,
So
that
actually,
does.
these they don't seem very complicated to me anymore.
And how about your particle flow nonlinear filter it's orders of magnitude faster than the standard particle filters for the same accuracy. How did you go about developing that? And what were some of the main challenges you had to overcome?
Yeah, that one started out with a puzzle. I first heard about particle filters about 25 years ago. The U.S. Air Force invited me to a little working group at Wright-Patterson Air Force Base, and we heard some briefings by people who had applied particle filters. And the claim was that these particle filters would beat the curse of dimensionality, meaning that they would get good accuracy as a filter, but for very high dimensional problems without exponentially exploding computational complexity. And that just sounded wrong to me intuitively. In fact, my education at Harvard taught me that you weren't going to be doing that with this class of algorithms. So I looked into it, and sure enough, it was wrong. We did numerical experiments, and we published them a couple of years later, showing very, very clearly that these particle filters did not beat the curse of dimensionality. In fact, and later, I think about 3 years, no, 5 years later, Peter Bickel at Berkeley, University of California at Berkeley, proved mathematically that any algorithm like a particle filter must suffer from the curse of dimensionality. And the problem is actually very serious and generic. It's not that they suffer from the curse of dimensionality for difficult problems that somebody cooked up to torture particle filters, but rather they suffer from the curse of dimensionality for even the simplest, nicest, smoothest problems, like the Kalman filter problems, for which we know the exact answer. So now the question was, so okay, that was good. So now I had this intense desire to understand why. Why did the particle filter suffer from the curse of dimensionality? So I teamed up with two guys at Lincoln Laboratory, Hody Lambert and John Weatherwax. In fact, I think they came to me because they wanted to get on board this technology. So we had dinner together every week at a nice Italian restaurant in Lexington, Massachusetts. And the tablecloths were paper. They were brown paper tablecloths, so we could write on them. And so we wrote out our equations and our block diagrams and our ideas on these big brown pieces of paper. And we'd take them home if they didn't have too much spaghetti sauce spilled on them already. And we designed a very, very, what we thought was a very good new kind of filter, particle filter, that would not suffer from the curse of dimensionality. Because what we had done was I had told Hody and John how to solve a what I thought was the tough part of the problem, exactly analytically in closed form, just with formulas. So it wouldn't suffer from the curse of dimensionality. So they programmed it up, they tested it, but and it worked reasonably well for certain problems, but it definitely did not overcome the curse of dimensionality. And then the question is why? because I thought I had solved the tough part of the problem. So there was another part of the problem. It's called Bayes' rule. Bayes' rule is the way to compute a probability density of the state conditioned on all the measurements. And computing Bayes' rule is just the simple multiplication of two functions. So it's very, very low computational complexity. So no normal person would ever think that Bayes' rule was causing the problem, and yet it was. You can draw a simple cartoon to show why. And the reason that it was causing the problem was that the particles in this d-dimensional state space were generally in the wrong place, not because they were evil particles or somebody had made an error or a bug, but rather just generically, it's extremely hard to know where to put the particles in this big d-dimensional space when d is large. So now the question is, so here's the third question. How do you fix that problem? Well, the obvious intuitive answer is you move the particles to the correct part of d-dimensional state space. But it's not so easy to do that because we don't know where that part is. But we can do it by breaking the problem up into little pieces. And so we invented a way of doing that. And but to do it, so we basically invent a law of motion. We invent a law of motion. It's just like physics. It's like the force of gravity or magnetism or electromagnetism. It's like a force field that moves the particles incrementally towards the region that they should go. And the theory is basically exact. So it's a beautiful theory. The only rub is that you have to solve a partial differential equation in order to derive the law of motion that you need. And so that's an interesting challenge. And by solving partial differential equation, I don't mean numerical solution. Solving a partial differential equation in d dimensions, where d is a big number, like 10 or 20 or 100, is just totally not in the cards. So you have to solve it analytically. But that's what I was taught to do at Harvard. That was one of my favorite hobbies, solving partial differential equations analytically. And this particular partial differential equation is my favorite partial differential equation. It's the Fokker-Planck equation. So we managed to do that, in fact, and we did it in successively more general, more useful, more sophisticated ways. After about 4 years of successfully better and better solutions, I was on vacation. I was on a bus ride with my wife in the Sahara Desert in Morocco with a bunch of birders called twitchers. The Brits call birders twitchers. And so this was a very, very long bus ride because the Sahara Desert is pretty big. So my wife and I had exhausted everything we were interested in talking about. So I took out my notebook and started to try and solve this partial differential equation again. And I noticed a very, very nice thing that happens if you make certain identifications in this partial differential equation, from which our most powerful solution of particle flow arose. And then after that, I recognized that there's actually a much, much, much more general mathematical theory by Misha Gromov, famous Russian mathematician, which explains the success of what I had done on that bus in the Sahara Desert. Gromov's theory is really different and avant-garde and outlandish. It violates all the rules that you're taught about in school of solving partial differential equations. It starts by saying, well, if I have a sufficiently underdetermined system of partial differential equations, then this very, very nice solution that I had discovered on the bus in the Sahara Desert always exists. So you can just look for it, and you're guaranteed to find it if you look hard enough. So this is solving underdetermined partial differential equations is a no-no in textbook PDE theory. In textbook partial differential equations, they start by saying, well, a well-posed problem in partial differential equations has to have a unique solution. And also the solution has to exist, and also the solution has to be uh, regular, that is smooth or continuous. But Gromov's theory violates that by having PDE that's very, very useful, but nevertheless does not have a unique solution. So you have to pick a solution. And I'm pretty good at picking the right solutions.
Wow, that was quite the project. And so we mentioned previously you received the IEEE Dennis J. Picard Medal for Radar Technologies and Applications. How does that award compare to the other ones? That seems like a big honor.
It is. It's the biggest, I think. To begin with, it's more money. It's $20,000. For me, as a working engineer, $20,000 is a very nice prize. And then it's a gold medal. I'd never gotten a gold medal before. And of course, you always want to test it. So we gave it the acid test with both nitric acid and hydrochloric acid. So it is, in fact, genuine gold.
I thought you were just supposed to bite it.
That's what the you always see in those pirate movies. Yeah, they bite the doubloons, but that doesn't ensure. It could be made of lead or some
True.
other soft. Yeah, I can make alloys that are quite soft that mimic gold. Yeah, that's the first thing you do. Yeah, you give it a good bite, and then you go to your dentist if there's any problem with that. And then the ceremony was lovely. The president of the IEEE and everybody else was there. Actually, just being surrounded by all these other wonderful people getting their awards on the same stage was terrific. I did get well, I've gotten a bunch of other awards. Like I got the Tom Phillips Prize from Raytheon. And that was given to me by Dennis Picard himself, and that was really special because Dennis knew exactly what I had done to win that prize. So he was the CEO of Raytheon at that time. So him handing me the prize was really, really special. And the Army gave me a prize that they call the Radar Scotty Award, which they gave me for saving them at least tens of millions of dollars, maybe more, because we had built a very fancy high tech radar system. One of the other contractors told the Army they thought that the angular measurement accuracy was not sufficiently good to satisfy the system requirements. So I heard that and I thought, no, that's not true. So I did a very simple back of the envelope formula. It's literally one envelope will hold the whole calculation. This is plugging in numbers to the Poisson probability density, and assured the U.S. Army, no, there's absolutely no problem with this radar the way it is now. It doesn't need any fixing at all. And of course, the contractor, whose name shall remain nameless, um, they had come to this what I thought was an erroneous conclusion by using a big, complicated Monte Carlo simulation. So I told the Army, look, get somebody to look for a bug in that Monte Carlo simulation. So they did. They had a third party, not from Raytheon, not from this big other contractor, but from a little contractor down in Huntsville, Alabama. And sure enough, this guy found the bug in this complicated Monte Carlo simulation to the delight of the US Army and to the delight of Raytheon management and to my delight and to the chagrin of this big nameless defense contractor.
Was hoping to get a big contract, but saved them a lot of
Well,
money.
actually, we would have Raytheon would have gotten 100. No, I guess the other contractor would have gotten a slice of it, but we would have gotten
Yeah.
most of it.
So I wanted to ask you some questions just about, radar in the industry in general. How has the introduction of high power GaN devices over the past decade affected the system testing and performance?
Well, GaN is wonderful. It's like magic. You get an order of magnitude more power density, and but I view GaN as simply, from my perspective, a evolutionary improvement. I mean, remember, I started with silicon solid state transmit devices in many decades ago, and at UHF and L band, and then that evolved into gallium arsenide. So at X band and S band, and then of course that evolved into GaN today. I expect that tomorrow or next year, or 5 or 10 years, we'll have some other materials like diamond. Diamond has a much higher band gap, much better thermal conductivity than any of the other materials, but it's difficult to dope it and has other technical issues. So of course, solid state high power transmit devices for radars. That's what I live and breathe, and the radars are incredibly reliable. And huge availability. I mean, we run some radars 24 hours a day, 365 days a year, and the only reason that the radar would ever fail is 2 or 3 redundant computer systems for some reason, not because of the radar hardware. This radar phenomenally reliable compared to high power tubes. But there are issues you have to overcome solid state radars. In particular, the transmitted waveforms are much longer. Like instead of a microsecond pulse, you might be transmitting a millisecond or a 10 millisecond long pulse. And at high PRFs, this means the radar occupancy is a great burden. You have to manage that very carefully. So but also you'd like to keep the PRF constant, ideally, and doing all of that, juggling all 3 of those balls and keeping them in the air at once is a tricky real-time radar scheduling issue. But we figured out how to do that quite efficiently. Another fun thing with solid state radars is the enormous range Doppler coupling. That is, when you measure range with the radar, you think, oh, I'm measuring the time delay, and hence I'm measuring the true range to the target. Absolutely not the case after pulse compression with a linear FM waveform. You get an apparent time shift after pulse compression that can be on the order of seconds or even tens of seconds. So that all the algorithms have to be adjusted to account for that. Actually, we've exploited that effect. So it's not just a curse, it's a blessing in many ways for us. Another issue is if an object is rotating, you can see the rotation and it'll modulate the apparent range because of range Doppler coupling. The third physical issue is the rocket exhaust plume. Say that you're tracking a Minuteman missile in boost as a test, and you see its rocket exhaust plume, say with a UHF radar. Well, that rocket exhaust plume is going in exactly the opposite direction of the rocket. It's going at around 2 or 3 kilometers per second, mean velocity, opposite from the true velocity of the solid rocket body. And this great, but what you've measured with a linear FM waveform with a solid state radar is something that is a scrambled mess of that true physical situation. So you have to untangle that, and that was a lot of fun. I could spend a whole hour talking on that subject. And we learned a lot of physics in doing that.
And so there's a lot of talk about AI and machine learning these days. What kind of effect is that going to have on radar systems for the future?
Well, it absolutely will have an effect on radar systems, but for us, AI is nothing new. I was doing AI 40 or 50 years ago in the real world. Remember, I took Marvin Minsky's course at MIT in AI, and even if I hadn't taken Marvin Minsky's course, we were absolutely forced to put artificial intelligence into the real-time software for waveform selection, for beam steering, for data association, for allocation of radar resources and computer resources. The artificial intelligence that's in our real-time software, even many decades ago, was way, way, way beyond what you would imagine by reading just academic papers on this subject. For example, Professor Simon Haken at McMaster University up in Canada wrote an IEEE paper about 20 years ago, and the title of his paper was Cognitive Radar, but by which he meant a radar that would use artificial intelligence to do the sorts of things that I just explained. Well, Professor Haken, this was 30 years after we had been doing this in the real world in many operational, important, expensive, big radar systems. Despite that, Professor Haken, in fairness, he didn't know about what we had done. And why didn't he know? It's because I was unable to publish any of this work. In fact, I still can't publish. I consider this my very best work that I've ever done, but I can't publish it. And you can't publish it because of restrictions of ITAR. Much of it is classified, and also competition sensitive considerations. All issues prevent me from ever publishing a paper. I was invited to give a talk, a classified talk, classified at the secret level talk for the Tri-Service Radar Symposium about 20 or 30 years ago on this subject. And the people who invited me, I think, were from the US Army. But the Raytheon managers told me, no, Fred, please do not give away the crown jewels. We don't want our competition to learn, even though if I'd given a talk at Tri-Service Radar Symposium, the problems of classification, ITAR, and EAR would all be fine. And the only issue would be competition sensitive material. But that was a complete showstopper. Couldn't possibly give such a talk in good conscience. Another thing is, when we say AI and machine learning these days, it's generally synonymous with deep learning and neural nets. But deep learning and neural nets, at least today, it's not ready for prime time. And it also has very fundamental limitations, like there's no uncertainty quantification. That is, it might give you an answer, it might give you a decision or an estimate, but it won't tell you how good it is, or at least it won't tell you reliably, quantitatively how good it is. Another thing is it's not. There's no guarantee whatsoever that the output of this neural net, is optimal or anywhere close to optimal. There's no theory of optimality. There's no claim of optimality. There's no discussion of optimality. Whereas my business, what I'm paid to do is provide algorithms that are either optimal or as close to optimal as we can make it with approximations with the amount of money, schedule, and risk that we're willing to undertake. And then another thing is deep learning, for example, ChatGPT-4. ChatGPT-4 is a wonderful tool for certain things, but it's horrible at math and logic. It can do some very elementary things, but often gives a completely wrong answer on freshman math tests, for example. So what you need to do is marry it together with something like Wolfram Alpha. And that has been done. That was done over a year ago. But that's still not That's still not anywhere close to good enough. Another problem is ChatGPT 4 and similar large language models. I mean, you input lots and lots of stuff, papers, everything from the internet, but there's no curation of that material. That is, there's no one telling the ChatGPT 4, this is good stuff. You can trust this stuff. And this other stuff is doubtful, dubious, or maybe highly likely to be wrong. ChatGPT 4 has no sense of truth. It doesn't understand what the word truth means. So you've probably heard all sorts of horror stories. Like for example, last week in the newspaper, the latest version of ChatGPT 4, when you ask it how to make a recipe for pizza, it will include in the list of ingredients glue. And many people were, and that was so serious that Google pulled the product. They're not. They've pulled it back and said, "Whoops, we've got to fix something." But you shouldn't get me wrong. I'm not saying that computers and AI and machine learning will never be up to snuff for making significant contributions in radar. There are certainly niche applications today, like in prognostics and other very specific, well-constrained environments. But also, in the long run, in the long term, I have absolutely no doubt that computers are going to eclipse humans at science, math, and engineering. I don't know how long it'll take, but it might be 10 or 20 or more years. But furthermore, the deep learning that you see today, like ChatGPT 4, it's not Bayesian. I believe the correct way forward for deep learning is Bayesian deep learning, or even just Bayesian particle flow. In fact, we have patents and papers and talks. You can just Google that, Google my name for Bayesian deep learning, and you'll find what we're talking about. So in the future, I expect, this should be pretty good in the long term.
Excellent. Well, thanks a lot, Fred, for talking with me today about your career in radar technology and some of the other fields that you've explored. To our listeners, you can find more podcasts at podcast.microwavejournal.com. Thanks for listening.